Hey guys, welcome back to another Chem 115 lecture video. In this video, we will look at three more examples for solving the pH of a weak monoprotic acid or a weak monoprotic base. Each example highlights different ways that the given values could be presented to you, and we are going to learn how to work through these types of problems and learn how to solve them. So let's go ahead and get started. So for our first example for this video, let's go ahead and read the question. What's the pH of a 0.175 molar solution of dichloroacetic acid in water? And so in this scenario, they gave us the pKb. So the pKb of this compound is 9.7442. And we're going to go ahead and address the percent ionization and the pOH and the concentration of hydroxide ions after we determine the pH of the solution. And so since we're trying to solve for the pH of the solution, we need to determine the hydrogen ions, the concentration of hydrogen ions at equilibrium. And so to do so, we need a mass action expression. So let me take that back. We need to solve for the change or for the value of x. And the way that we can do that is by writing the mass action expression. And so for us to write the mass action expression, we need the ice table. And for us to write an ice table, we need a balanced chemical equation. So very similar to part one, we're going to go ahead and work backwards. We're going to write the balanced chemical equation first, then the ice table, then we're going to determine the mass action expression, solve for x, and we're going to determine the equilibrium concentration of the hydrogen ions. And then from there, we can go ahead and calculate the pH of the solution. So let's go ahead and write the balanced chemical equation for this reaction. Since we're working with dichloroacetic acid, the chemical formula is already given to us. So we're just going to go ahead and write it below. And so here we have HC2, HCO2, Cl2. And so to write a chemical equation for the ionization of the proton in dichloroacetic acid in water, we need to identify what our ionizable hydrogen is. And so here we have two hydrogens in this chemical formula. And very similar to what I discussed in part one of this lecture video series, the ionizable hydrogen is either found, it's either found at the very front of the chemical formula to represent the cation. Another way that it could be presented is if this hydrogen was written at the very end, like this. And so since this hydrogen is written in the front, it's written in the position of the cation, we know that this first hydrogen is going to be our ionizable hydrogen. So let's go ahead and erase this second highlight. And so since this is an acid, when we place that in water, some fraction of the total population of dichloroacetic acid is going to ionize, producing H plus in solution. And so since we're placing everything in water, the physical state of matter is going to be aqueous. And the conjugate base for dichloroacetic acid is simply going to be C2, HCO2, Cl2. And once again, we have a negative charge. So if you recall from part 1 of this specific topic, once you separate the cation from the anion, you have to indicate its charge. Cool. And so we need to determine whether or not dichloroacetic acid is a weak acid or a strong acid, because it's going to determine what we are going to place in our change, in the row for change in our ICE table. And so one way that we can do this is look at the Ka value, or the equilibrium constant value. In this problem, notice that I did not give you guys the exact equilibrium constant for dichloroacetic acid. I actually gave you guys its pKb. In this case, it's going to be 9.7442. And so before we start working with this value, we need to take a step back and kind of understand what's going on in our balanced chemical equation. And so since this is dichloroacetic acid, right, the main point being an acid, when we're taking this compound and when we ionize the hydrogen, the first hydrogen in this compound, we're separating it to produce proton and the conjugate base. And so the forward reaction is reflective of the equilibrium constant Ka. So if you guys recall, Ka is the ionization constant for acids specifically. And so looking at what I gave you guys in the problem, I gave you pKb. And so somehow we have to convert pKb into Kb, and then we'll have to convert Kb into Ka, so that the equilibrium constant that we write down in our mass action expression is reflective of the ionization of dichloroacetic acid. All right, so let's go ahead and determine the value for Ka first before we even touch anything else. Since the value for pKb is 9.7442, we can determine the Kb by using one of the formulas that we covered a couple weeks ago. And so remember that if you have anything, if you P anything, and I'm talking about the letter P, then what you're doing is you're taking the negative log of that specific value. So P, Kb, is a negative log of Kb. And so if we move terms around, if we solve for Kb, we're first going to move this negative to the other side. So here we have negative pKb is equal to the log of Kb. And so to get rid of the log, we're going to use the base 10 function to cancel it out. And so to determine the Kb, we're simply going to punch into our calculator second log to bring up the base 10 function, and it's going to be raised by negative pKb. And so notice that I gave you guys the value for pKb. Sometimes I see students plug the pKb into Kb. Please don't do that. You guys are going to plug that value in to what it represents. Since it represents pKb, you guys are going to plug that over here. So in other words, we're going to take base 10 of negative 9.7442. And so since this form has already been negative logged, for sig figs, we want to report 4 significant figures because there are 4 places after the decimal. Okay. So once again, I'll do it here. So since there are 4 places after the decimal, when we write our answer down for KB, we have to report 4 significant figures. And so if we plug that into our calculator, our KB value is going to be 1.802 times 10 to the negative 10. Now that we've solved for KB, we're going to go ahead and convert KB into KW using the relationship Ka times KB is equal to 1.008 times 10 to the negative 14. And I don't think I've stated it in the problem, but we're going to go ahead and assume that this solution is happening at 25 degrees Celsius. If it's happening at a different temperature, then this value needs to change. So the KW needs to change to whatever the value is for that specific temperature. And you guys can go ahead and see the different KW values at different temperatures if you look through your lecture notes. All right, so we're going to go ahead and plug in this value into KB such that Ka is equal to 1.008 times 10 to the negative 14. Divide this by 1.802 times 10 to the negative 10. So I kind of skipped a couple steps here. I went ahead and plugged in the value for KB, and to solve for Ka, I'm going to go ahead and divide KB to the other side. And so the acid ionization constant, or Ka, it's going to be 5.59378, and I'm sure there's a whole bunch of numbers, times this by 10 to the negative 5. And so since we have 4 sig figs in our quotient, on each side of the quotient, the numerator and denominator, we're going to go ahead and report 4 significant figures in our final answer. And so since the digit past the last significant digit is greater than 5, we're going to go ahead and round that number up. So the Ka is going to be 5.594 times 10 to the negative 5. So now that we solved for our acid ionization constant, we can go ahead and look at the magnitude. And so since the magnitude is far, far greater than 1, so far, far less than 1. So since Ka is far, far less than 1, then we know that this compound, this dichloroacetic acid, is going to be a weak acid. And so when we develop our ice table, the value that we're going to place in change is going to be X, not the initial concentration. If the equilibrium constant, the acid ionization constant, is far, far greater than 1, then the change would be the initial concentration. All right, so now that we have the value for Ka, let's go ahead and develop our ice table. So I is initial concentration, C is change, E is the equilibrium concentration. And so since everything is aqueous, we're going to consider all reactant and product species in our mass action expression. And so according to the problem, we have a 0.175 molar concentration of dichloroacetic acid. And so we're going to go ahead and put in 0.175 molar to represent the initial concentration of this compound. And so since this dichloroacetic acid is a weak acid, we're going to go ahead and in our change, we're going to write minus 1x. And once again, since we're just separating the hydrogen from its anion, everything is a 1-to-1-to-1 ratio. Since the problem did not give us any initial concentrations or initial amounts of the proton and the conjugate base of dichloroacetic acid, we're just going to go ahead and leave them blank. However, in the change, we know that we're going to consume some amount of dichloroacetic acid, producing some amount of product. In this case, is going to be plus 1x and plus 1x. Okay. And that 1x is coming from the coefficient. So for the equilibrium concentrations, we can go ahead and write expressions for it by simply adding the column downwards. So this is going to be 0.175 minus x. You don't really want to move this the other way around, so please don't put in x minus 0.175. That's going to throw off your guys' answers. And so you always want to add downwards from top to bottom. And so this is going to be x, and then this is going to be x. So 0 plus x is x, 0 plus x is x. All right, and so the next thing I'm going to do is going to write my mass action expression, because now I have, equilibrium expressions for the equilibrium concentrations. And so since this is Ka, the acid ionization constant, that's going to equal to the concentration of the proton raised to the first power, because there's a coefficient of 1, times this by the conjugate base of dichloroacetic acid. Once again, raised to the first power, because the coefficient is 1. Then last but not least, I'm going to put the reactant in the denominator. So this is going to be dichloroacetic acid. And once again, we're going to go ahead and raise it to the first power. So now that we have the mass action expression, or the equilibrium law, for this specific reaction, we're going to replace all of these reactant species and these products with what they represent at equilibrium. In other words, we're going to plug in X into hydrogen. We're going to plug in X into the conjugate base of dichloroacetic acid. And then we're going to go ahead and plug in this expression into dichloroacetic acid. And so we're also going to plug in the value for Ka, which we just solved for here. Okay. Oops. And so Ka is going to be 5.594 times 10 to the negative 5, which equals to x raised to the first power times this by x raised to the first power. Divide this by 0.175 minus x. And so if we reduce the numerator, so x times x is going to be x squared. If we leave this alone, then so if we leave this alone, if we move all the terms, we're going to get a quadratic. And so we want to determine if we can ignore this denominator, this x in the denominator. And we can go ahead and assess that by determining whether or not the statement is true or false. The initial concentration is going to be far, far greater than the equilibrium constant. In this case, since we're working with an acid, it's going to be Ka times 100. And so if this statement is true, then we can go ahead and ignore the x in the denominator. So that's just letting us know that the actual change is going to be really, really small, where it really doesn't affect the initial concentration significantly. And once again, we don't want to ignore the x in the numerator because notice how like we're not comparing this x to another number. So it's not like 0.175 plus x or something like that. So that means that any value that we get in the numerator is going to be significantly greater than 0. So we want to keep the x in the numerator. And so since the initial concentration is 0.175, and if we multiply 100 by the value of Ka, which in this case is going to be 5.594 times 10 to the negative 5, we're going to get 5.594 times 10 to the negative 3. And so if I express this as a decimal, I'm going to move the decimal place 3 times to the left. So that's going to be 0.005594. So now that I have everything expressed as a decimal, I can quickly see that 0.175 is far, far greater than 100 times Ka, which is 0.005594. And so since this statement is true, I can go ahead and ignore the x in the denominator, allowing us to simplify our mathematical expression as 5.594 times 10 to the negative 5, which is equal to x squared, over 0.175. And so at this point in time, since we only see x in the numerator, we're just going to solve this problem algebraically. And so we're going to go ahead and multiply that 0.175 over, and then we're going to take the square root of both sides. And so at some point when you guys are working this out algebraically, you should get this in your work. So 5.594 times 10 to the negative 5 times this by 0.175, which equals to x. Okay. So if you take the square root of the product of what's inside, you guys are going to get 3.128 times 10 to the negative 3. And so since there are 3 sig figs here and there are 4 sig figs here, so 3 sig figs is less than 4 sig figs. And so I'm going to go ahead and put a mark right above the 2, letting me know that I'm just going to record or report the first 3 sig figs that I see. And so here in this case, since the last number is an 8, we're going to go ahead and round this value up. And so this is going to be 3.13 times 10 to the negative 3. And that's going to give us the answer for x. So now that we have the value for x, we're going to go ahead and plug this back into our ICE table. But we want to work smart. And so revisiting the question, we're trying to determine the pH of the solution. So the only thing that'll give us the pH is the concentration of the proton at equilibrium. And so if we're taking a look at our chemical formula, our chemical equation, this is our dichloroacetic acid. And so that's not really going to give us the equilibrium concentration of the hydrogen ion that we're looking for. Same thing with the conjugate base. So the only thing that's going to give us the pH is if we solve for the concentration of H+ at equilibrium. And so that value is going to be determined by x. So it turns out that the x that we solved for through our mass action expression is going to be the equilibrium concentration of hydrogen ion. And so we're going to go ahead and take this value x and state that it's going to equal to the concentration of our protons at equilibrium. And that value is going to be 3.13 times 10 to the negative 3. And so since we're talking about molarity now, or concentration, we need to go ahead and add the molarity unit. Awesome. And so what we're going to do next is, so now that we have the equilibrium concentration of hydrogen, we're going to go ahead and determine the pH of the solution, finally addressing the question. And so the pH is always equal to the negative log of whatever that substance is. In this case, it's the hydrogen. And so we're going to go ahead and plug in 3.13 times 10 to the negative 3. And so if you put that in your calculator, you guys are going to get 2.5046. And I'm sure there's some more numbers after. So since there are 3 significant digits in the value of the concentration of hydrogen ions, we're going to report 3 places after the decimal for our pH. And so since this last number is a 6, that means we're going to go ahead and round the 4 up. So the pH for this solution is going to be 2.505. Awesome. All right, so now that we figured out the pH, we can actually figure out the POH. And so we can go ahead and use this relationship. The pH plus POH is equal to 14. And so if we plug in the value for pH, which is 2.505, we can go ahead and solve for the POH by subtracting it over to the other side. So the POH is going to be 11.495. Okay, and so once again, I'm just solving for POH. So I took 14 and I subtracted it by 2.505, giving me a POH of 11.495. And if I wanted to determine the concentration of the hydroxide ion, we can go ahead and use the definition of POH to figure that out. So the negative log of the concentration of OH. And so if I solve for this specific term or variable, we need to move the negative to the other side. So negative POH equals to log of the concentration of OH minus. Then we're going to go ahead and take the base 10 of both sides, giving us an expression stating that if we take the base 10 of the negative of POH, that's going to give us a concentration of the hydroxide ion at equilibrium. All right, and so since the POH is 11.495, we're just going to go ahead and plug that into this area. So 10 to the negative 11.495 equals to the concentration of OH minus at equilibrium. And so you guys can go ahead and plug this into your calculator. So take the base 10, so second log, and then type in negative 11.495. And you guys should get an answer of 3.19615. And I'm sure there's some other digits after, times 10 to the negative 12. And that's going to give you the concentration of OH minus. Now when we're converting from POH back to concentration, we want to pay attention to sig figs. since there are 3 places after the decimal, that means that we are going to report 3 significant figures in our final answer. And so we're going to take this 6 and we're going to round it up. And so our final answer is going to be 3.20 times 10 to the negative 12. And that's going to give us a concentration of OH minus. And so if you guys are looking at the pH is 2.505. Since we have a pH that's less than 7, this solution is going to be considered acidic. Another way that we can determine if it's acidic or basic is by comparing the concentration of H plus and OH minus. And so the magnitude is times 10 to the negative 12 for OH minus, which is far, 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 far less than the magnitude of the concentration of H plus, which is times 10 to the negative 3. And so since this has a higher value than times 10 to the negative 12, that's another way that we can assess whether or not the solution is acidic, basic, or neutral. Okay. So the last thing that we're going to determine is the percent ionization. Okay. So we want to assess what percent of the total population of dichloroacetic acid will actually ionize to produce the product. And so here in this case, we want to figure out the change and the initial concentration because we're going to take the ratio between the two. And so according to our ICE table, our initial concentration is 0.175. And so the 0.175 is going to represent the total concentration. So that's going to be in the denominator. And so the change is dictated by the value of x, which is going to be 3.13 times 10 to the negative 3. So I'm going to go ahead and put the change in the numerator. So 3.13 times 10 to the negative 3. And then we're going to go ahead and divide this by the initial concentration, which is 0.175. And last but not least, we're going to go ahead and multiply it by 100. And so let's go ahead and put that into our calculator. So 3.13 times 10 to the negative 3. And we're going to divide that by 0.175. And then we're going to multiply that by 100. And so the percent ionization is going to be 1.79 rounded to the correct number of significant figures. So only 1.79% of the total population of dichloroacetic acid will ionize to produce H plus and the conjugate base. So that's pretty small. And so a small percent ionization once again reflects the idea of this compound being a weak acid. If it's a strong acid, then the percent ionization is probably close to 100%. Okay. So we have several ways to assess the strength of the acid or the strength of the base. We can either assess it using the value for our Ka. We can assess it by looking at our percent ionization. And I also had you guys memorize all your strong acids and all your strong bases. So basically, if it's not on that list that I had you guys memorize, then it's most likely going to be a weak acid or a weak base. All right, so that pretty much finishes this specific problem. And so how this problem is different than the previous problems that we worked through is just this beginning step. And so in this case, I gave you guys the pKb. And so you should be able to determine what the Ka is if you convert pKb to Kb, and then from Kb into Ka. And so you guys can do so. You guys can go ahead and solve for the Ka by converting pKb into Kb. And then once you guys have the Kb, use this relationship Ka times Kb equals to Kw. And so this Kw is at 25 degrees Celsius. And then just divide the two values to get your Ka. Cool. So let's go ahead and look at another problem. So for number 5, we have an unknown monoprotic acid, and this time it's going to be symbolized as HA. And it has a percent ionization of 2.25%, when 2.78 grams of this unknown monoprotic acid is dissolved in 755 mils of water at 25 degrees Celsius. And so if the molar mass of this monoprotic acid is 36.453 grams per mole, we want to go ahead and determine the pH of the solution. And we're going to go ahead and determine the acid ionization constant and convert that into pKa. And we're also going to determine the Kb and the pKb. Okay. All right. And so since we want to determine the pH of the solution, so we've done enough of these problems where we should automatically know the general solution map and how to get the pH of the solution. And so for us to determine the pH of the solution, we need to know the concentration of H plus at equilibrium. And for us to do so, we need to determine the value of the change from the mass action expression. And for us to develop our mass action expression, we need an ice table. And for us to develop our ice table, we need a balanced chemical equation. Okay. And so if we perform these general steps, we should be able to determine the pH of the solution. So let's go ahead and do the first step, which is writing a balanced chemical equation. Since the identity of our compound is a monoprotic acid, we're going to go ahead and represent that as HA. And since we placed 2.78 grams of it in water, we know that it's going to dissolve, so its physical state of matter is going to be aqueous. And so when this monoprotic acid dissolves, a small fraction of it is going to produce the proton, and it's going to produce its conjugate base. Okay. And so since we are working with an acid, if we're looking at the forward direction, we know that we're ionizing our acid. And so therefore, we need to have an equilibrium constant that's reflective of it. And so, long story short, we need Ka. All right. And so let's go ahead and build our ice table. So we have I, C, and E. Since everything is aqueous, we're going to consider all reactant and product species in our mass action expression. And so the initial concentration has to be in molarity. But if you look at what the problem gave us, it gave us 2.78 grams, and it was dissolved in 755 milliliters. And so we can't really plug in 2.78 grams in place of molarity, so we have to do some conversions. And so I'm going to go ahead and do these conversions on the side over here. So if you have 2.78 grams of HA, we want to essentially convert this into molarity of HA. And if you recall, molarity is a ratio of moles over liters. And so if we can somehow get moles of 2.78, or I'm sorry, if we can somehow convert 2.78 grams of HA into moles of HA, we can go ahead and plug that into our numerator. And then for our volume, which is liters, we're going to go ahead and convert 755 milliliters into liters and put that into our denominator. And then once we have those two values, we're going to go ahead and divide them to get molarity. And so to go from grams to moles, we're going to have to use the molar mass of that specific compound. And so 2.78 grams of HA, it's going to be converted into moles of HA. And since we want to convert from grams to moles, that lets us know that we have to put this specific unit in the denominator. So grams of HA is going to be placed underneath. And so whenever you guys have moles and grams or grams and moles, that should remind you of your molar mass. And so in this case, the molar mass is 36.453 grams per mole. So let me just highlight this. So 36.453 grams per mole. Okay. And so I see a lot of students make very simple fundamental mistakes. And if you make a mistake at this point in the problem, everything is going to be wrong. And so one way to lessen the mistake of where to put the 36, whether it goes into the numerator or denominator, I want you guys to go ahead and extend this line. And I want you to notice that this 36.453 is connected to grams. And anything that's not shown in the denominator, you can always put a 1. So that's going to be 1 mole. And so when you're placing this conversion factor into your dimensional analysis, we're going to put 1 mole, or we're going to put 1 in the numerator because it's connected to moles. And then we're going to go ahead and place 36.453 in the denominator. And so this is telling us that we're going to divide these two values. And when we divide these two values, we're going to get 7.63 times 10 to the negative 2 moles of HA. And so that's what we're going to put in the numerator to determine the molarity of this solution. And so let me just put this down here. So molarity is equal to 7.63 times 10 to the negative 2 moles. Now I'm going to go ahead and divide this by the volume, and the volume must be in liters. And since our volume in the problem is 755 milliliters, remember milli is times 10 to the negative 3. So we're just going to take this invisible decimal and move it 1, 2, 3 places to the left. And so that's going to be 0.755 liters. Now when we divide both of these values, and when we're reporting this to the correct number of sig figs, it's going to be 0.101 molar concentration. And so this is going to be our initial concentration for HA. Now that we have the concentration, we're going to go ahead and figure out what the change is. And so we have two options. Either the change is going to be equal to the initial concentration, which defines a strong acid, or the change is going to be minus X, which defines a weak acid. Now, looking at this problem, notice that the Ka was not given to us, nor was Kb or pKb or pKa. And so we don't know what HA is. It just says it's an unknown monoprotic acid. So it could be a strong acid, it could be a weak acid. However, if we look at the percent ionization, notice that it's only 2.25%. Anything that is very small in terms of percent ionization, it's basically describing a weak acid or a weak base. And so by looking at the percent ionization, we can go ahead and determine that this monoprotic acid is a weak acid. And therefore, the change is going to be described as minus x. Now, if you balance the entire chemical equation, everything is 1, 1, 1. And so this is going to be minus 1x. And so if we consume some amount of HA, we know that we're going to produce some amount of H plus and some amount of the conjugate base. Now, to write our equilibrium expression, we're just going to simply add downwards. And so 0.101 minus x, is going to represent the equilibrium concentration of HA. Very similar for if we add downwards. And by the way, the problem did not give us any initial concentrations of H plus or A minus. So therefore, it's just going to be plus x and plus x. Cool. So now that we have our ice table built, we can go ahead and write the mass action expression. And so since this is the ionization of an acid, we are going to use Ka, not Kb. So Ka is going to equal to, and I'm going to just jump some steps here. It's basically H plus raised to the first power times this by A minus raised to the first power, divide this by HA raised to the first power. So the mass action expression that we're going to get is x to the first times this by x to the first, divide this by 0.101 minus x. And so the reason why I'm skipping steps is that I've done enough of these to hopefully show you how I got to this point without showing every single step. And so Ka is, actually, we don't know what the value of Ka is. And that's something that we need to solve for. And so if you look at the problem, the Ka was not given at all. And so we're going to go ahead and leave that as a question mark. However, we can reduce the rest of this expression to x squared over 0.101 minus x. And so here in this case, since we don't have the value of the Ka, we don't really know if we're going to ignore this x in the denominator. And so this is kind of tough because we have essentially like 3 places where we don't know numbers. We don't know the value of Ka, we don't know this value in the numerator, and we don't know this value in the denominator. And so we're kind of in limbo here. And so let's go ahead and look back at this question and see if we can use another value to help us further our calculation. So let's go ahead and look at percent ionization. And so they told us that the percent ionization is 2.25%. And so if you guys recall from previous problems, the percent ionization, there's a formula, and that's going to represent the change, or C. So I've kind of abbreviated the value. I've abbreviated change as C in previous problems. Divide this by the initial concentration. Times this by 100. And so if you look at our ice table, our change is representative of x. And so we can go ahead and plug in x in change. And this percent ionization, we already know that value. That's 2.25%. That's coming from the problem. And here the initial concentration is something that we've already calculated, which is 0.101. And so when we substitute all of these parts, so we have 2.25 equals to x over 0.101 times this by 100. And so if we solve for x, or for the change, then that means that we know the value of x in this mass action expression. And we can go ahead and determine the Ka, and we can also determine the value for x, which will represent the equilibrium concentration of hydrogen ion. And so the first thing that you're going to do is you're going to divide by 100. Okay. And so pretend that this x is, I don't know, a princess trapped inside a castle. So for you to get to the princess, you want to work outwards in. And so since this times 100 is furthest, if you will, from x, we're going to go ahead and divide that to the other side. So that's going to give us 0.0225 equals to x over 0.101. And so to solve for x, we're just going to go ahead and multiply that value to the other side. And the answer that we're going to get is 2.27 times 10 to the negative 3. So now that we've solved for x, we can actually answer two items. So remember that x represents the change. And if you look at the equilibrium expressions for this hydrogen ion, it's also x. And so by solving for x, we've actually already determined the hydrogen ion concentration at equilibrium. And that's going to be 2.27 times 10 to the negative 3 molar. So now that we have the equilibrium concentration of hydrogen ion, we can go ahead and start solving for the pH without having to really determine this value from the mass action expression. So this is going to be pH is equal to negative log of 2.27 times 10 to the negative 3. And so if you take the negative log of that answer, that's going to give you 2.64397. A whole bunch of other numbers. And so in regards to sig figs, there are 3 sig figs in this value. And so when we take the negative log of it, we need to keep 3 places after the decimal. And so this 9 is going to round that 3 up, giving us 2.644 is our pH. And so if you look at the value for our pH, it's less than 7. So this solution is going to be acidic. Cool. So the last, so here we've addressed the pH. And so notice that we didn't exactly work, we didn't figure out the pH through conventional methods as seen in previous problems. And so we didn't really use the mass action expression to determine the H+, and that's okay. You don't have to follow this solution map for every single problem. This solution map might change based on the given values that it gave us. And so we just wrote this generic solution map just so that we have like a point that where we can start with. So like a reference point. All right, so the last thing that we need to solve for is Ka, pKa, Kb, and pKb. And so the only way to solve for the Ka is through the mass action expression. And in this case, we're going to go ahead and plug in the value of x into this mass action expression. And remember that value for x is going to be 2.27 times 10 to the negative 3. So that means that the value of Ka is equal to 2.27 times 10 to the negative 3 raised to the second power. Okay, so substituting that x with this value. And then I'm going to go ahead and divide that by 1.01 minus x. In this case, that's minus 2.27 times 10 to the negative 3. Great. And so please don't forget to square your numerator. That's another common mistake that I see students make. And so if you guys plug in all of this into your calculator, you guys should get 5.21918 times 10 to the negative 5. And so since there are 3 sig figs, we're just going to go ahead and just report 3 sig figs. Actually, let's see here. Let's look at this operation first. So we have 0.101, and then we're going to subtract by 2.27 times 10 to the negative 3. So that's 2 zeros before the 3, or I'm sorry, before the 2, and 2, 7. Okay. And so to confirm whether or not we are going to use 3 sig figs, since we're subtracting these two, we have to pay attention to the rules of subtraction for sig figs. And if you recall from first semester general chemistry, it's just the least number of places after the decimal. And so it looks like if we were to subtract these two, we would have to report 3 values. So let's go ahead and take the difference of that. So 0.101 minus 0.00227. So that's going to give us, let's see here, 0.09873. So 1, 2, yeah, that's negative 2. So it looks like the if we take the difference, it's going to be 0.099. And so this value is what's going to go inside our denominator. So what we get is 2.27 times 10 to the negative 3 squared over 0.09873. And so I'm just going to put a mark above the 8, letting me know that that's how many significant figures that I'm supposed to keep for that value. Now, let's see here. The reason why I didn't put in 0.099 is because I don't want to really lose accuracy, if you will. But I do want to be precise in reporting the number of significant figures. I'm not I don't think it's going to affect our answer too much. Whether or not you put a 0.099 or a 0.09873. But long story short, this is telling us that we have 2 sig figs when we perform the division. And here we have 3 sig figs in our numerator. And so when you guys are squaring something, you guys are just multiplying that number by itself. So it's like 2.27 times 10 to the negative 3 times 2.27 times 10 to the negative 3. So that's still, 3 sig figs in both scenarios. And so it looks like 2 sig figs is the least. And so in our final answer, we're going to go ahead and just keep the first two digits. So it turns out that the value for Ka is going to be 5.2 times 10 to the negative 5. So I'm just going to go ahead and write that down here. So Ka is equal to 5.2 times 10 to the negative 5. Great. And so once again, looking at the magnitude of Ka, it's times 10 to the negative 5, which is far, far less than 1. So this is telling us that this compound, HA, is going to be a very weak acid, which once again is highlighted by the percent ionization, which is 2.25%. All right, so now that we solved for Ka, let's go ahead and solve for pKa. Now remember, whenever you take the P of something, you can take a P of the house, P of a cat, P of a dog, P of a number. That's just basically saying in mathematical speak that it's the negative log of whatever it is that you're taking. And so pKa is equal to the negative log of Ka. And so pKa is equal to the negative log of 5.2 times 10 to the negative 5. And so if you guys plug in this value in your calculator, so I'm just going to do it in mine very quickly. So negative log of 5.2 times 10 to the negative 5. That's going to go ahead and give me 4.28399. Then there's a whole bunch of sixes. And so since we have two sig figs in our original value, since we're taking the negative log of it, we want to report two places after the decimal. So the pKa is going to be 4.28. Notice that the 3 is rounded down. Perfect. And so now that we have the pKa, we can go ahead and determine the pKb. And so if we're assuming that this is at 25 degrees Celsius, we can say that the pKa plus the pKb is equal to 14. And if we plug this number in, 4.28, and we subtract it, so we're going to take 14 minus 4.28, it's going to go ahead and give us the pKb. And so if I put in my calculator, I'm going to get 9.72. And so the pKb is 9.72. And so if you guys recall from 2 weeks ago, the higher your pKb value or the higher the pKa value, the less likely it's going to be strong, if you will. So since since the pKa is 4.28, 4.28 is very close to 0. So this is telling us that this is more of an acid and less of a base. So since its pKb is 9.72, which is higher than its pKa, this is telling us that this compound is more acidic than it is basic. Okay. All right, so the last thing that we're going to solve for is the Kb. And so we can solve for the Kb in one of two ways. We can solve it by using the definition of pKb, or we can go ahead and use the Ka. And so I'm going to go ahead and use the Ka. So since the Ka is 5.2 times 10 to the negative 5, so Ka times Kb is equal to Kw. So if it's 5.2 times 10 to the negative 5, Kw at 25 degrees Celsius, it's going to be 1.008 times 10 to the negative 14. And so KB is going to be the quotient between this number. So it's going to be 1.008 times 10 to the negative 14. Divide this by 5.2 times 10 to the negative 5. And so the value for KB, I'm just going to go ahead and plug this one into my calculator. So 1.008 times 10 to the negative 14. And I'm going to divide that by 5.2 times 10 to the negative 5. So with the correct number of significant digits, I'm going to get a KB value of 1.9 times 10 to the negative 10. Okay. And once again, if you guys compare the magnitude of our Ka and the magnitude of our Kb, notice that 10 to the negative 5 is closer to 0 compared to times 10 to the negative 10. So therefore, since our Ka is much greater than our Kb, we know that this compound is going to be much more acidic than it is going to be basic. Cool. And so we went ahead and solved each part that the question is asking us. Here in this case, if the percent ionization is already given to you, remember that you can solve for the change directly if you solve for the numerator in that formula. Awesome. So let's go ahead and take a look at our last example for this topic. And then we're going to go ahead and explore other topics in acid-base equilibria. And that's going to be presented in other lecture videos. And so for number 6, if the Ka of a monoprotic acid, HX, is 5.55 times 10 to the negative 2, what is the pH of a 0.192 molar solution of this compound? And there's really no other follow-up questions, and you guys will see why. But if you wanted to determine percent ionization, the pOH, and the concentration of OH, or like the pKa, or pKb, or Kb, you guys have the tools to be able to work that out on your own, and you should be able to do so. All right, so let's go ahead and just focus on the problem. And since we want to determine the pH of this solution, once again we have to think about our canonical solution map, where the concentration of H plus at equilibrium needs to be determined, and we can go ahead and get this from solving for X in our mass action expression. And then to develop our mass action expression, we need the ice table. And to develop our ice table, we need a balanced chemical equation. Okay. And so once again, this is just like a generic solution map. Just like what we saw in problem number 5, we didn't actually follow this solution map to get to the pH, but it helps us, start off working this problem. It gives us some type of guide. And we can go ahead and adjust the solution map if we need to do so, depending on how the problem is presented to us. All right, and so the first step is to develop our chemical equation. Since this is a monoprotic acid, that's HX. We're going to go ahead and take HX, put it in water, and some fraction of this is going to ionize to H plus and X minus. So that's the conjugate base. And so to determine the pH, we need to develop our ice table. So I, C, and E. And so let's see here, we need to identify the initial concentration of HX, and that's going to be 0.192 molar. And it didn't really give us the initial concentration for H plus or X minus. So we can go ahead and just ignore all of that stuff. So here in this case, since all of the physical states of matter for each chemical species in this chemical equation is aqueous, we're going to consider all 3 of them in our mass action expression. All right, cool. So let's go ahead and talk about change. Remember there is two options for change. It can be minus x, or it can represent the initial concentration. And for us to figure out which is which, we need to determine if this is a weak acid or a strong acid. In this case, since the magnitude of the Ka is times 10 to the negative 2, we can go ahead and say that this is a weak acid. And since this is a 1:1:1 ratio, this is letting us know that we have a minus 1x in our change for hx, plus x for h, and plus x for x minus. Should have changed the x to something else. It's okay, we'll work with it. So the equilibrium expression for hx is going to be 0.192 minus x. And the equilibrium expression for h plus is going to be x. And the equilibrium expression for the conjugate base, x minus, is also going to be x. And so we're going to go ahead and develop our mass action expression. And so it's going to be a ratio of products over reactants raised to their coefficient to represent the power. And so let's see here, Ka is going to be H plus raised to the first times this by x minus raised to the first over Hx raised to the first power. Once again, they're all raised to the first power because the coefficient is 1, 1, 1. So now we can go ahead and just plug in the equilibrium expressions into the mass action expression such that Ka is going to be 5.55 times 10 to the negative 2. That's going to equal to x times x, which is x squared, over 0.192 minus x. All right, and so very similar to the previous problems, we want to determine if we can ignore the x in the denominator. Is this change going to be significant? If it is going to be significant, then we cannot ignore it. If the change is going to be insignificant, if it's a small enough value where it's not going to change the initial concentration too much, then we can ignore it. And so to answer this question, we're going to go ahead and prove whether or not this statement is true or false. Is the initial concentration far, far greater than Ka times 100? And so since the initial concentration is going to be 0.192, and if we take the Ka value, which is 5.55 times 10 to the negative 2, and if we multiply that by 100, will that statement still hold true? And so when you multiply this by 100, this is basically times 10 to the positive 2. So they're going to cancel each other out. And so what we get is 0.192 is far, far greater than 5.55. Is this statement true or false? And so this statement is false. And so since the statement is false, can you ignore the change in the denominator? And the answer is no, you cannot. And so if you cannot, then that means that you guys have to solve for the value of x using the quadratic equation. And so for us to lead up to that point, we need to move everything to one side such that one side of the equal sign is going to be a 0, and the other side is going to have all of the other expressions. And so let's go ahead and multiply this term to the opposite side first. So for 5.55 times 10 to the negative 2 times this by 0.192 minus x equals to x squared. And so we're going to go ahead and distribute the 5.5 times 10 to the negative 2 to both terms. Sometimes I see students only do it for one term and not the other. So please make sure you guys revisit your rules for distribution. And so if I if I distribute that 5.55 to both terms, I get 1.07 times 10 to the negative 2 minus 5.55 times 10 to the negative 2. And that's going to equal to x squared. Whoops. And so since our x squared is positive on the right-hand side, I'm just going to go ahead and move both of these terms to the right side of the equal sign. For me, it's just aesthetics. I'd rather have a positive x squared rather than a negative x squared. But you guys should be able to get the answer if you subtracted x squared to the left side. But for now, I just like to keep my x squared positives. And so I'm going to go ahead and move both of these to the other side such that I'll get 0 on the left-hand side. And I'm going to get x squared plus 5.55 times 10 to the negative 2 power times x minus 1.07 times 10 to the negative 2. And so I'm going to scoot this guy just a little bit further to the left. Now, if I put in a coefficient in front of that x squared, it's a 1. This lets us know that this is my value a. This whole term in front of x is my value for b. This whole term, including the negative sign, is my value for c. Okay. And just to be consistent, I'll go ahead and include that positive sign for that 5.55. So now that I've identified a, b, and c, I'm just going to go ahead and use the quadratic formula. And so this is going to be negative b plus minus the square root of b squared minus 4ac. Okay. So it's kind of presumptuous for me to extend that square root all the way out. So let me just go ahead and put it this way. And we're going to divide this by 2a. So everything here is a multiplication. So there's a multiplication between the 4 and the a and the c, and a multiplication between the 2 and the a. And so wherever we see a, b, or c, that's where we're going to plug it into this equation. And so here we have negative of b. So this is going to be negative 5.55 times 10 to the negative 2 plus minus b squared. So this is going to be 5.55 times 10 to the negative 2 squared minus 4 times a, which is going to be 1, times this by c, which is negative 1.07 times 10 to the negative 2. And so all of this is going to be divided by 2 times a, or 2 times 1, since the value of a in this case is 1. Now I'm just going to go ahead and reduce everything that's inside that square root. It looks very beastly, so to speak. And so I'm going to go ahead and do this by parts, square this, multiply this, and then subtract at the very end. Okay, so once again, I'm going to perform this action first, perform this action second, and then I'm going to perform this operation third. And if you guys do it correctly, you guys will get 4.588 times 10 to the negative 2. At this point, I'm not even going to worry about sig figs. There's just too many things that's going on. And so I'm going to go ahead and divide the denominator by 2. So now if we take the square root of this value, you guys will get negative 5.55 times 10 to the negative 2 plus minus 0.214. And then just to not lose accuracy, I'll go ahead and put in 19. So I'm just going to go ahead and put in a mark above the 4, letting me know that I'm just going to keep 3 sig figs. All right, so I'm going to go ahead and divide this by a 2. And so now that I've reduced my quadratic equation, I'm going to go ahead and take a look at the positive and the negative version of this specific work or equation. So if I'm looking at the negative version, it's going to be negative 5.55 times 10 to the negative 2 minus 0.21419. Divided this by 2. Now, if you think about it, remember change is representative of concentration. And so if you were to subtract these two values, you would get a negative number. And so there's no way that a negative value can represent the change if it's reflective of concentration. And so therefore the negative route in this scenario is going to not lead us to the true value of x that we are searching for. In other scenarios, in other problems, it might, but for this problem, it's not because there's a negative in front. And so, for example, if this was 5.55 times 10 to the negative 2, and let's just say that this was a smaller number, like 0.021419, then it's going to give us a positive answer, which could be the correct solution for our problem. But in this case, it's a negative number, and so x can't be negative, so move on. And so looking at the positive route, we have negative 5.55 times 10 to the negative 2 plus 0.21419. And divide this by 2. And so real quick, I'm kind of lazy at this moment to figure out the actual significant figures for what's going on in underneath the square root. And so I'm just guessing at this point that there's 3 sig figs. There's probably 2 sig figs. But for now, let's just say that there's 3. So once you guys have this setup, notice that this is a larger number. This 0.21419 is a larger number than negative 5.55 times 10 to the negative 2. And if you were to subtract them and divide it by 2, the value for this x, or the value for this solution, is going to be 7.93 times 10 to the negative 2. Cool. And so if this is the value for x, this is the value for the change. And so once we figured out what the value of x is, we can go ahead and plug it into our ICE table. So basically anywhere you see x, you guys can go ahead and plug in 7.93 times 10 to the negative 2. Once again, we want to work smart. We want to figure out what the pH of this solution is. And so we can calculate the pH of the solution by determining the equilibrium concentration of hydrogen ion. This is our hydrogen ion right here, and therefore its equilibrium concentration is just represented by X. And so this value that we got is representative of the concentration of hydrogen ion at equilibrium. And so since now this is representative of concentration, we need to put in molarity. So to determine the pH of the solution, we're just simply going to take the negative log of the number. And therefore the pH is going to be 1.100. And so there's 3 sig figs, 3 decimal places. So this is our answer. So looking at our values, we can already tell that this solution is going to be very acidic. From this point on, you guys should be able to calculate the pOH. You should be able to calculate the concentration of OH. And based on the Ka values that is given to you, try practicing how to calculate pKa, Kb, and pKb. Okay. All right, so that's pretty much it for this video lecture. Hopefully you guys were able to follow my train of thought. Let me see here, I'm going to scroll up. So I do really encourage you to go back and replay this video and just kind of fast forward where you guys see the questions with no work, with none of my work shown, and see if you guys can solve these problems on your own. And, you know, obviously the solution is already videotaped for you, or it's recorded for you. And so if you're kind of stuck at a specific problem, you can play the video to that specific point just to help you move forward in your own solution. And so the next video that I'm going to post, it's going to move on to the next topic in this chapter, which is being able to predict whether or not a solution is going to be acidic or basic just by simply looking at the chemical formula. All right, guys, so hope you have fun. Stay safe out there, and I'll talk to you the next video that I post. See ya.